As elements go, helium is kind of an all-star. It's used in medicine as an essential component of MRI machines. It's important in the manufacture of silicon wafers for computers. Arc welders use helium during the construction of ships and cars and buildings. It even exhibits some weird behaviors that are studied in cutting-edge physics. Not to mention, helium has probably been a part of most of the parties you've ever attended, inside those balloons. There's just one problem. Helium is so useful that we're quickly burning through our limited supply. Some recently discovered subterranean reserves ensure that the situation isn't critical, but at the rate we currently use it, we have 1 or maybe 2 centuries worth of helium left. And we didn't even know it existed 150 years ago. The good news is, we do know how to make more. The bad news is, that process can level an entire city. You're listening to the Episodic Table of Elements, and I'm T.R. Appleton. Each week, we'll take a look at the fascinating stories behind one element on the periodic table. Today, we're taking a deep breath and looking at element 2, helium. In the early 19th century, Joseph von Fraunhofer was the finest lens crafter in the world. He was a true prodigy, displaying outstanding skill from a young age, despite never receiving much of an education. To assess his work, he'd focus a newly ground lens on a candle's flame. And because his tools were so precise, he could see details that no one had before. One of the things this allowed him to discover was that when a chemical element is heated until it glows, it emits a unique pattern of light, acting like a fingerprint that precisely identifies that element. The tool that did this was called the spectroscope, and it was integral to the success of early chemistry. It allowed for accurate analysis of mineral samples taken from the Earth, and it directly led to the discovery of cesium and rubidium in 1861. But a few years later, 2 great minds had the same idea: to turn the spectroscope toward the sky. In 1868, Pierre Janssen and Norman Lockyer each independently analyzed the light of the sun by spectroscope, and they discovered something strange. A series of Fraunhofer lines, as the light patterns came to be called, that didn't match any known chemical. This was another case of multiple discovery, as discussed last episode. Janssen noted this with curiosity, but only Lockyer was bold enough to name his discovery. Since it was discovered in the sun, the element inherited its name from the Greek word for sun, helios. Few elements on the periodic table are as aptly named as helium. Some amount of it was created during the Big Bang, along with all the hydrogen in the universe, and a small amount of lithium. But the sun makes its own fresh supply, right on site. A star is born when a cloud of hydrogen gathers in space, the atoms attracted to each other by gravity. Eventually, they pack together so tightly that strange things begin to happen. As the cloud increases in density, pressure and heat begin to rise. Hydrogen atoms start smashing together and glomming onto each other, a process called fusion. When 4 atoms of hydrogen slam together, they create a single atom of helium. This helium atom is slightly less massive than the 4 hydrogen atoms combined because a tiny amount of that mass is converted to energy in the form of light and heat. This is why the sun shines. This fusion reaction is happening constantly in stars like the sun. With every second that passes, 700 million tons of hydrogen are burned into helium ashes. Amazingly, we've been able to replicate this process here on Earth, but only by detonating hydrogen bombs. And when that happens, helium conservation is probably the last thing on anyone's mind. This transmutation within the sun can only go on as long as there's a supply of hydrogen to convert into helium, and in about 5 billion years, our sun will run out. But it won't snuff out like a flame at that point, no. Something much more interesting starts to happen then. When there's no more hydrogen to burn, the sun will use its helium as fuel, smashing those atoms together into carbon and oxygen. Stars more massive than the sun will continue in this way, eventually creating elements as heavy as iron. The sun is too small for that to happen, but something else very interesting will happen when it starts burning helium. It'll become what's known as a red giant, mostly because, well, it will become red and gigantic. In fact, it'll grow so large that the orbits of Mercury and Venus and then Earth will all be inside the radius of the sun. But don't worry, the oceans will boil away and Earth will be rendered uninhabitable a long time before that happens. Let's zoom in to see how helium is a little more complex than what we looked at last time. You might remember that hydrogen is a pretty simple little atom. The simplest, in fact, with a single electron buzzing around a single proton. Helium, meanwhile, has 2 protons, because remember the number of protons defines the element. But a new kind of particle has joined the protons in our nucleus, the neutron. While electrons carry a negative electrical charge, and protons have a positive one, neutrons, as the name suggests, are entirely neutral with no electrical charge whatsoever. This turns out to be pretty important. Without neutrons padding the space between positively charged protons, they would repel each other, and the atom would rip apart. In the entire universe, nothing more complex than hydrogen would be able to form. While they don't carry an electrical charge, neutrons are pretty massive, contributing about as much to an atom's weight as a proton does. This is why helium has an atomic weight of approximately 4. There are 4 particles in the nucleus, and each one has a mass of about 1. But an atomic number of 2. Only 2 of them are protons. Electrons, you might remember, are extremely small and add almost nothing to an atom's weight. Neutrons are the final piece of the atomic puzzle. Every element we examine from here on out will consist of some number of protons, neutrons, and electrons, and that is it. Speaking of electrons, the 2 that helium possesses are what make it act so differently from hydrogen. Helium's the first of the noble gases, so called because they're too prim and proper to be seen mingling with any of those other low-class elements. Seriously, helium, neon, and the others in Group 18 practically never combine with other atoms to form molecules. Remember how hydrogen has 1 electron that creates a shell around its nucleus? It turns out that shell is only half full. It can actually fit 2 electrons in that shell. And it really, really wants to find another electron to fill its shell. This is why hydrogen is so reactive. It's so desperate to fill its electron shell that, if you just add a little heat, 2 hydrogen atoms will make an arrangement with any nearby oxygen atom, and they lend each other some electrons. This provides a full electron shell for the 2 hydrogen atoms and 1 oxygen atom, thus H2O. It sounds quite diplomatic, but from our perspective, that's exactly the reaction that's responsible for hydrogen's explosive nature. Helium, on the other hand, already has 2 electrons in its shell. It is quite satisfied, and won't be needing any electron handouts from other more volatile atoms, thank you very much. It is a pure individualist, needing nothing from nobody. With lithium, things get pretty exciting again, but we'll save that for next episode. Helium may be 4 times as massive as hydrogen, but it's still the second lightest element in the universe. Much like hydrogen, any amount that finds its way into the atmosphere will slip the surly bonds of Earth, floating away into outer space. This is why people were skeptical of Lockyer and Jansen's discovery of helium within the Sun. With no sample on Earth to test against, it was practically impossible to verify. Some scientists dismissed it as no discovery at all. But other people saw an opportunity to play the element game a little fast and loose. In 1879, there was a solar eclipse, and some scientists turned their spectrometers toward the outer edges of the sun. They found new, unidentified lines in the sun's corona. Much like helium, this was presumed to be a new element, fittingly dubbed coronium. But Annie Besant and Charles Leadbeater took things to the next level. In 1908, they published one of chemistry's strangest books. It was called Occult Chemistry: Investigations by Clairvoyant Magnification into the Structure of the Atoms of the Periodic Table and Some Compounds. It was a landmark text of the Theosophy movement, and that was a mystical philosophy that took hold in the late 19th and early 20th centuries. Its founders didn't dispute contemporary findings of science, but rather they tried to incorporate that into their divine wisdom. Of course, this was alongside their beliefs in spiritualism, astral projection, and seances. It's important to note that this was an unprecedented time in history. For the average person, the line between the scientific and the spiritual certainly seemed to be blurring. Scientists were discovering a plethora of invisible forces that governed our lives. X-rays, radioactivity, and the atomic structure that underlies everything in our world. Why should those exist, but not telepathy, clairvoyance, and our immortal souls? In fact, what if these mysterious new forces somehow linked the world of the spiritual with the world of the physical? From our current perspective, it's easy to scoff at these beliefs, but this was a way that people dealt with a confusing world that was changing every day. It helped that the Theosophists capably mimicked the style and tone of scientific papers. Occult chemistry was filled with diagrams, measurements, and jargon that sounded pretty reputable, until it really didn't. For instance, at one point the authors write, "A chemical atom of ozone appears as an oblate spheroid, with the contained spiral much compressed and widened in the center. The spiral consists of 3 snakes, 1 positive and 2 negative, formed in a single revolving body. On raising the chemical atom to the next plane, the snake divides into 3 and, being enclosed in its own egg." There's a lot of weird stuff in there, but those are some precise observations to declare. But this was a time before electron microscopes and particle accelerators, so how did Besant and Leadbeater conduct these observations? They claimed that by using their third eye, they could directly observe the world at the atomic level. It was during one of these observations that the Theosophists discovered a new element of their own. In occult chemistry, they described it like so. "Occultum was observed by us in 1895, and finding that it was so light and so simple in its composition, we thought that it might be helium. When, however, helium itself came under observation in 1907, it proved to be quite different from the object before observed. So we dubbed the unrecognized object occultum, until orthodox science shall find it and label it in proper fashion." The two never actually intended to deceive people. As one blogger wrote of the two, "Leadbeater and Besant are often called charlatans, but they were not. Their idiocy was sincere." Now, obviously, orthodox science never did find evidence of occultum, and coronium wasn't a new element either. That just turned out to be what iron looks like when you heat it to a few million degrees Celsius. Neither was nebulium or lutetium, or dozens of other proposed elements that turned out to not actually exist. But it's worth acknowledging that the periodic table, concrete as it looks now, existed for a long time in a state of flux and chaos, and with that came all the mistakes, quick conclusions, and even opportunism that accompanies any burgeoning field of science. It's half a miracle that we even know which elements exist with any certainty whatsoever. And that's a great thing. Because if you're going to collect something, it sure better exist. Last time we did a little kitchen chemistry to add hydrogen to our collection of chemical elements. Helium is much easier to collect. Just go to your local party supply store and ask for a balloon. But you might worry that such a vendor may be disreputable. The party store only needs helium that's good enough to keep a latex balloon afloat for less than a day. Who knows whether it's quality helium, the kind that a discerning collector would want. Luckily, those who trade in chemical elements, professionally I'm talking about chemists here, chemists have a system in place to grade the quality of their product. But it's not as simple as saying, this helium is 95% pure, because we're mostly dealing with much higher purities than that. Many industries need to know whether a sample is 99.997% pure or 99.999% pure. It's very precise work that they're doing. Since repeating 999 so many times would be confusing and unhelpful, pure elements are given grades like 4.5 or 5.0. The number before the decimal point says how many nines are in the percentage grade purity of the element, and the number after the decimal point represents the number after the last 9. So grade 4.5 helium is 99.995% pure, while grade 5.0 helium has 5 nines followed by a 0, or 99.999%. Grade 6 helium is as pure as it gets, and it's used in the ultra-precise work of semiconductor manufacture and chemical research. And I'm sorry to say, the lowest purity of helium is casually called balloon grade. But you have to admit that chemical applications don't get much more frivolous than party decorations. But unless you're a true perfectionist, you don't need to worry about a contaminated supply. It's actually considerably more difficult to provide low-grade helium than 5 nines. The reason for this is because helium is most often compressed and stored in tanks, so it can be transported as efficiently as possible. When it's compressed beyond a certain pressure, helium liquefies, and this liquid helium is, by its nature, extremely pure. It would actually be more expensive for suppliers to introduce impurities. So rest easy, knowing that you can easily get a reasonably pure sample of helium for your collection. Just make sure to store it in something more leak-proof than a latex balloon. Thanks for listening to the Episodic Table of Elements. Next time, we'll investigate the highs and lows of lithium. Music is by Kai Engel. To read show notes and the transcript for this episode, comment and learn more, visit episodictable.com/helium. This is T.R. Appleton reminding you to find a way off-planet before we're consumed by the flames of a dying sun.